Hello everyone, my name is Alex Hintz. I'm a Bridge Program Fellow with the Engineers in Action Eswatini program, and today I'm going to show you how we go through a soil classification exercise when we conduct our technical surveys for your bridge sites. Now, soil classification is a tricky thing in itself, and we do not have access to a full laboratory test to perform on the soil. So what we do here is our best estimate using our engineering judgment and using our experience in the field so far to create or to compile as much information as we can and present to the student teams in order for you to estimate an allowable bearing capacity. That is the main objective of classifying the soil and providing you with this information to obtain that allowable bearing capacity, which is important because it tells you the strength of your soil and whether or not the loads that are exerted on your soil will be withstood by the soil. So let's go ahead and look at the technical survey form. This is page 2 of that form, which we provide to you. And drawing your attention to the chart that we fill out here, you'll notice that there are 4 different soil sample locations that we test for. And these are broken down into the left and right sides, the anchor and foundation locations. Now keep in mind that these locations are preliminary, that it's an estimate of where we anticipate the foundation or the anchor to be located. It's not based on the final design, it's based on a preliminary design which we look at here in our office in order to roughly place where the anchor and foundation will be. And it's okay to only have an approximate location and test the soil in that approximate location because we can assume that if the soil in one spot it has certain characteristics that within a few meters radius the soil will most likely be very, very similar to where we tested. So it's okay if we test in kind of just general areas as as opposed to the final location for the foundations or anchors. You'll notice that the first soil sample which we tried to test was at the left anchor, and continuing with the idea of the soil test in a certain radius, we weren't able to access the proposed location or the approximate location for the left anchor. And this might have been because there was brush in the way, there were trees, there were bushes. Some reason we could not physically access where that anchor was intending to go. And sometimes this happens before a site is cleared fully of all the vegetation and we show up to do our survey. Sometimes we have a little bit of uh, just tricky time navigating through any brush that's still there. So in this case, we couldn't access that anchor location, but it's okay because we could access the left foundation location. And we can assume that the soil at the foundation will be very similar to the soil found at the anchor location. It may differ slightly, and if that's the case and if that's a concern, then we could lean more towards a conservative approach when assigning an allowable bearing capacity. But moving on now to the next column in the table, the visual classification column. This column here, roughly, or the data that we collect here, roughly follows the USCS classification system for soil. And you can look up and research more about that, but briefly, the USCS classifies soil based on the grain size of the particles in that soil. And it's uh, broadly defined in 2 major categories. We have fine grain soils and coarse grain soils, also sometimes referred to as granular soils. And the difference between fine and coarse grained or fine and granular are the amount of material that passes the number 200 size sieve. And so you can look up more about that, but the terms that we use in our visual classification are loosely based off of that. Again, we don't have a full laboratory sieve set to do a thorough test and classify it based on grain size, but we look at the soil with our eyes and we pick up the soil and we interact with it in a limited capacity just to get a feel for what are the grain sizes in this soil? Is it mostly sand? Is it mostly gravel? Is it mostly clays or silts? And from that visual classification, we can move further and deeper into the testing. So you'll notice for soil sample number 2 here, we classified visually as clayey sand. Now, the first term in the classification represents the minority component of that soil. So clay is there was a little bit of clay in the soil. The second term in the visual classification represents the majority of the soil composition. So clayey sand simply means that most of that soil appeared to be sand and some of it appeared to be clay. But most of it was sand, a little bit was clay. And same idea with gravelly sand for the third sample location and silty sand for the fourth. Now moving on to the next column, the toughness test classification. This is a test which we conduct using a sample of soil which we collect and just collect in the palm of our hand. Then we introduce some moisture to that soil sample, and then attempting to roll that pile of mud, so to speak, into threads of soil, which are at least or at most 1/8 inch diameter thickness. So I'll show you a picture of this because you may be wondering what this looks like. So here's a picture from this survey site of the toughness test that we performed on this soil. So I took a soil sample in the palm of my hand, introduced some moisture, and then attempted to roll it into threads. And you'll see from the picture here that I did achieve rolling that soil sample into 1/8 inch diameter threads. So what this tells us is that the soil has a high percentage of fine-grained particles. So going back to our chart where we filled out the initial visual classification, visually we saw this was mostly sand with a little bit of clay. But doing the toughness test classification, we actually discovered that it was mostly fine-grained soils, and the minority component was coarse-grained soils. So this should tell us that, or this is just to illustrate that the visual classification is a preliminary classification. It's just based on us looking at the soil and using our best judgment to determine what the composition of that soil is. Moving on to the toughness test should confirm or conflict with our initial assumption here, and then we can move forward with more confidence in knowing what types of soil or what types of material the grain size particles make up that soil. So I'll move to the flow chart, which we have in that same technical survey document, just so you can get a visual of the process again. And starting from the beginning, just briefly locating the testing sites, anchor and foundation on the left and right sides, removing topsoil until undisturbed soil is found, then moving into the visual classification as granular or coarse or fine-grained soils. And again, that's a description or that's a classification describing the size of the grains, the size of the particles in that soil. And so if we visually classify it as granular soil, then we move down to the left. If we visually classify as fine soil, which we did for that number 2 soil sample, then we move on to the 3 millimeter log toughness test. If we're unsuccessful with that test, and I'll show you what an example of that looks like. If we're unsuccessful with that test, then we know that that's granular soil. So we move back to the granular uh, part of the flow chart. But if it is successful, then we know that it is a fine-grained soil, and most of the particles are uh, 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 clay or silty particles. And so we move on to the next test, which I'll get to briefly. But I mentioned the unsuccessful 3 millimeter or 1/8 inch toughness test. And here's a photo of what something like that would look like. So I took a soil sample in my hand and introduced some moisture and attempted to roll that into threads. But the soil, the composition of it just wouldn't allow that. It would break apart and not achieve those 1/8 inch threads. And this is the result of attempting to roll that, but not being successful. So moving back to our chart here, you'll see that for the second soil sample that we tested, yes, we did achieve those 1/8 inch logs, and that was the photo that I showed earlier. For the right anchor and foundation locations, we were not able to achieve the 1/8 inch diameter logs, and that was the second photo that I showed you of the soil that was just crumbled apart in my hands. We weren't able to achieve it. So that tells us that we were correct in our initial assumption about these being coarse-grained soils comprised mostly of sand. So after we do the visual classification and the toughness test classification, then we always move to our final test, which is a 13 millimeter rebar penetration test. And going to the flowchart just very quickly, just to show you that that is the last step in our surveying process for soil before we move on to estimate bearing capacities using our design value estimate tables. So the 13 millimeter rebar penetration test is simply taking a rebar about 1.5 meters long and a 13 millimeter diameter, and that's a half inch. It's also a half inch diameter in the US, and attempting to push that rod into the soil first by hand, just using your body weight and pushing the rebar down. And if that is unsuccessful, if you can't really penetrate into the soil that much using just your body weight, then you take a 5-pound hammer and strike the rebar 25 times and measure the depth of penetration. And you may be wondering where this comes from, and you may find some similarities between this test and a standard penetration test. And all I can say right now, just briefly, is that these are different tests. This one is not, it does not use the same criteria as the standard penetration test. That is a different test entirely. What we have adopted here by using the 13 millimeter rebar and the penetration has been practiced by a few engineers who have provided us with these design values and design estimates based on their experience working on small footbridge projects like these. So this test is adapted into something very specific, and it's not really based on that standard penetration or SPT test. But from this test, we can relate the data that we collect here, we can relate that to something that we're familiar with SPT end values and allowable bearing capacities and friction angles and so on. But the 13 millimeter rebar test is simply, again, pushing a rebar by hand or striking it with a hammer 25 times, recording the depth of penetration and whether it was achieved by hand pushing or by using a 5-pound hammer. And we also record the difficulty that was required to achieve that penetration. So, for example, on the second soil sample here, you'll see that we were able to do both a hammer and hand penetration, but the hand only made it 2 inches, and that was with medium difficulty. But the hammer made it 10 inches with medium difficulty. So you'll see why these numbers are important, as I'll explain that in the next video, showing you how to interpret this data and estimate a bearing capacity of your own. But for right now, that would complete the chart. This is all that we test while we're in the field at the site. We visually classify, then we move to the toughness test classification, and then finally we move to the rebar penetration test. And after completing all those things and taking the photos for you, we can take this information and using the design value estimate tables, which are in the appendix of the technical survey form, we can see, and I'll show you in the next video, how to go through these tables and assign allowable bearing capacities. But for right now, this was just an overview of the soil classification test that we perform in the field here in Eswatini, and check out the next video for the discussion on how to interpret this data and estimate allowable bearing capacities from it.